right, chapter 4. First part of chapter 4 deals with making sure you understand chemical versus physical changes as we move into talking about bonds. Remember, physical change is something that is a change in physical properties, easily reversible, whereas chemical change involves a change in the chemical formula and it's irreversible. Let's look at why. A candle burning has two great examples. It's got the physical change where your wax is melting, and it's got the chemical change. Now, the melting wax, when you first light your candle and you get that pool of wax, if you were to blow out the candle, the wax would harden. Okay, so it's easily reversible. However, over a long period of time, you'll notice that your wax in the candle gets consumed. And that's because your wax is combining with oxygen in the air to produce water and carbon dioxide, other gases. That's why the wax seems to disappear. It's because it's being converted to something else. That is a chemical change. Now, energy is what determines the change in matter. Okay, and so we've got two specific kinds of forces we need to talk about. Interatomic forces are forces that are within molecules. Inter meaning between, atomic referring to atoms. So these are the forces that are actually between atoms inside of a molecule. It's what holds a molecule together, so it's really strong. Chemical changes deal with interatomic forces, so they involve a much higher energy change. Intermolecular forces, on the other hand, are forces that are between molecules. These are forces having to do with the way molecules interact with each other, and they're very weak. Physical changes deal with the intermolecular forces, so it's a much lower energy difference. If we were to look at it on a graph, we would see that the energy change for physical changes is in the hundreds range, whereas the energy change having to do with chemical changes is in the 100,000s range. So if we look at atoms and we start to talk about chemical bonds, it's important that we understand that the atomic structure, even though we represent it as little balls, it's not actually little balls, okay? Keep in mind that the atom consists of a nucleus, very small, very dense in the center of an atom, and it's surrounded by an electron cloud, okay? The nucleus contains almost all of the mass. All right, but it's this electron cloud that we're concerned with when we start to look at chemical bonds. All right, if we review really quickly electric charges, remember that we have two types of positive charges, positive and negative. We know that opposite charges attract each other and like charges repel each other. So a positive and negative would actually be pulled closer together, whereas two negatives or two positives would be would repel each other, would force each other apart. When we look at bonds, okay, and we look at what actually makes a molecule, bonds are created by electrons. And there are two cases that we'll study in here. Bonds that are made by sharing electrons and bonds that are made by transferring electrons. Now there's two types, okay, two names for those. Covalent bonds, and that's where we share electrons, or ionic bonds. That's where electrons are transferred from one atom to another, which makes ions, and then those ions, which are oppositely charged, will be attracted to each other. Okay, looking at covalent bonds a little more closely, they are the strongest chemical bond, and that is because electrons are being shared in between atoms. So this is how molecules are made. Things like water, or oxygen gas, or nitrogen gas. Okay, O2, N2, H2O, NH3, CH4. These are all very strong molecules, and it's because each atom in these molecules wants more electrons than it has. And so these atoms will throw electrons into a pool and kind of share them. And so these atoms are now bonded together. They're held together very closely, tightly, and it's because neither atom wants to lose the electrons that they're now sharing. So extremely strong bonds. On the other hand, we have ionic bonds, which are much more weak than covalent bonds, and that's because electrons are being transferred. So there's no sharing of electrons. It's not that both atoms really want the electrons for themselves. It's that one atom wants to get rid of electrons and another one wants to gain electrons. So, for example, if we look at salt, sodium atoms will lose an electron, which when it loses that negative charge, it makes it more positive. And a chlorine atom wants to gain electrons. So when it gains that negative charge, it becomes negatively charged. So we have positive charges on the sodium attracted to the negative charges on the chloride, and it's this electrostatic attraction, electrostatic meaning attracted because of the charges, that holds it together, not making a molecule. So why do chemical bonds form anyway? Why do we have ionic or covalent bonds? And it's because everything wants to be more stable. Everything seeks stability. And if we have a lower energy value, that means something is more stable. And some bonded atoms will become more stable than if they were not bonded. For example, if we look at the energy of individual atoms, an individual oxygen and a hydrogen and a separate other hydrogen, their energy level is much higher when they're separated, as opposed to the energy level when it is a bonded molecule like water. And so because it's a lower energy level to be water, these individual atoms would rather be bonded and form a water molecule. Some elements are very reactive and some elements do not react. Reactive elements will form compounds easily, and we rarely find them in elemental form because they've reacted with things around them. Things like the group 1 elements or alkali metals, extremely reactive. There are some elements that do not react. They will never form compounds, and we always find them in elemental form. Things like the very last group of elements, the noble gases. And we can use the periodic table to help us predict reactivity of elements. If you look at the far column, right, where the noble gases are, they do not react at all. Okay, so let's exclude them. Then the column right next to the noble gases, and then the column all the way on the far left, are very reactive. As we move towards the middle of the periodic table, we get moderately reactive elements, but those elements that are on the outside edges, with the exception of the hydrogen or the noble gases, are very, very reactive. Okay, you can tell that from the chart. The periodic table can also help us predict bond types. Remember, covalent bonds are formed between elements that want to gain electrons, and so they share them, and those would be all the nonmetals. They all want to gain electrons. So covalent bonds are formed between two nonmetals. Ionic bonds are formed between nonmetals and metals, and that's because nonmetals want to gain electrons and metals want to give them away. So just looking at a compound's chemical formula, if everything's a nonmetal, you know it's a covalently bonded molecule. But if you have a metal and a nonmetal, you know that that's an ionic bond. Chemical reactions are what allow chemical changes to occur, and we describe chemical changes and chemical reactions using an equation. Here is an example of having two water molecules, and they can become two hydrogen gas molecules and one oxygen gas molecule. And you see the equation listed underneath. In a chemical change, we are starting with one set of substances and ending with a different set. So the reactants are the chemicals that we start with, and they are written on the left side. Products are the chemicals that we are ending with, and they are written on the right side. So reactants are the things that are reacting. Products are the things that are being produced. So it makes it a little easier to remember. Okay, here we have an unbalanced equation showing us that we start with H2O and we end up producing H2 and O2, but it's not balanced. All equations have to be balanced, and that's because, according to conservation of mass, a chemical reaction is not creating matter or destroying matter. So all of the atoms that we start with are the same atoms we're ending up with. The only difference is we've rearranged them. So looking again at our equation that has now been balanced, we see that we have two oxygens on the left, two oxygens on the right, 4 hydrogens on the left, 4 hydrogens on the right. We can see that the lines or the bonds have been changed, but our actual numbers of each type of atom have not. Okay, so the rules for balancing a chemical reaction equation we're briefly covering now because we're going to spend several weeks on this later on. We do not change the subscript numbers because that's part of the chemical formula. If we change those little numbers, that would change the entire molecule that we had. Okay, we also can change how many we have of them. So we change those numbers out front. Those are called the coefficient numbers. And this diagram here takes you through the unbalanced reaction and compares it with the balanced reaction. And again, I will go through step by step with you how to do that, but we're saving that for later on in the semester. It's important right now to understand what a balanced chemical equation means. Chemical equations are like recipes. The unbalanced equations will tell us what the reactants are and what the products are, but it doesn't tell us how much we need or how much will be produced. That's what a balanced equation will do. And the units for this equation are in moles. So we're, again, going back to that mole concept. Those of you that took AP Bio, photosynthesis reaction should look very familiar. And what this balanced chemical reaction actually means is 6 moles of water will react with 6 moles of carbon dioxide to produce 1 mole of glucose and 6 moles of oxygen. We can use moles then to calculate how many grams of the reactants are needed or how many grams of product will most likely be made. We use formula masses as conversion factors, and we can see that our total mass is conserved, meaning the total amount we had on the left is equal to the total amount we have on the right. And we'll practice doing this too, also again, in a few weeks. Some reactions that we see will absorb energy and some will release energy. And we saw this in class. You had felt some reactions. Some were releasing heat and some were absorbing heat, so they felt cold. One type of those reactions is called endothermic. And what that means is heat is entering the reaction. So it's absorbing energy. Energy has to be added. Photosynthesis is one of those types of reactions because it needs light. So it's taking the energy from the light to produce the reaction. Exothermic is what we call reactions that have heat being released. Heat is exiting the reaction. Respiration, which is what humans do, the opposite of photosynthesis, is exothermic. So we ingest sugar and breathe oxygen in order to make energy that our body uses. We need to think of things in terms of the system and the surroundings. Okay, so total energy flow has to be constant. Energy that's going in to the system has to come from somewhere, and energy that's being released has to go somewhere. So we think of the system as the reaction and surroundings as everything else. So in an endothermic reaction, energy is absorbed by the reactants, and that energy is coming from the surroundings. So the energy is flowing from the surroundings into the system, whereas exothermic is the exact opposite. The energy that's released by the products is then given to the surroundings. So the energy flow for exothermic is going from the system to the surroundings. So photosynthesis, endothermic, absorbs energy. Energy is going from the surroundings to the system, whereas respiration is exothermic. It is producing energy. So the energy is going from the system to the surroundings. I've lost the graphic. Okay. So reactions don't occur spontaneously on their own. Energy is needed to break the chemical bonds. And just like it takes energy to separate magnets, it takes energy to separate bonded atoms. Once the atoms have been separated, then we can mix them around and create new bonds and make new products. So activation energy is that energy needed to break bonds in the reactants so that atoms can recombine to make products. All right, so in an energy level diagram, we can see here is the energy level of the reactants up here, the energy level of the products is down here, and this tiny little bump in between the two is the activation energy. So some energy has to be added to get the reaction going, but once the reaction is going, it will continue to proceed on its own. The Chapter 4 homework that was assigned, 1 through 27, 36 through 39, 43 through 47, 50 through 54, 57, 58, and 71.